Linked lists are used to store elements called nodes. When we say that nodes are linked, it means that one stores a reference to another. In a singly linked list, you can only go forward, whereas in a doubly linked list, you can go both forward and backwards. Here is the implementation for a node in a doubly linked list that stores an integer. It contains a reference to the next node and a reference to the previous node. The way you iterate over a linked list is by getting the next node of the next node of the next node, and so on until you reach the end where the node is null. Generally, in a linked list implementation, the list will store the head and tail nodes, which are the first and last nodes of a linked list. In a linked list with a length of 1, the head node is the same as the tail node. Let's go over the time complexities of various operations in a doubly linked list with a head reference and a tail reference. To add an element to the front, it's O of 1 constant time. You create a new node, update the links between that node and the head, and shift the head 1 to the left. To add an element to the back, it's also O of 1 constant time. You create a new node, update the links between that node and the tail, and shift the tail 1 to the right. To remove an element from the front, it's O of 1 time, since you just set the head reference to the next element and remove the links. To remove an element from the back, it's also O of 1 time, since you just set the tail to the previous element and also remove the links. To remove an element from the middle, you just update the links. The next of the current becomes the next of the previous of the next becomes the previous of the current. This is also O of 1 time. Now, a doubly linked list is pretty efficient, but it takes up more memory than a singly linked list because you need to store 2 links instead of 1. In a singly linked list, the major difference is in removing the tail element. Since we only store head and tail nodes, if we want to remove the last node, we have to traverse the whole linked list again to get the second to last node, in which we can set that to the new tail and remove the link. You can think about how a singly linked list would work with the other operations. Linked lists are great if you don't know what size you need your list to be, since you can keep adding elements. While in an array, you have to increase the size of the array if you want to store more elements. Linked list nodes are all over the place in memory, only connected to each other by stored references. So when you use linked lists, the nodes aren't actually next to each other. They look more like a bunch of scattered dots. Before we end, here's 2 tricks you might find useful. To reverse a singly linked list, store 1 reference to the previous node, 1 for the current node, and 1 for the next node. Set the next node of the current to the previous node, and set the current node to the next node. Repeat until you reach the end. To find the middle of a linked list, you can use a fast and slow pointer. Set 2 pointers that both point to the first node. One pointer will move twice as fast as the other. That means on each loop, one jumps 2 and the other jumps only 1. Once the faster pointer reaches the end, you've reached the middle on your slower node. And that's all I really found useful for linked lists. Thanks for watching, see you in the next one.